Welcome everybody to the 7th episode this year, the second episode in season 3, if you like. We will today, with guest speaker Eric Beckert from Fraunhofer IOF and Arne Benfeld from ficonTEC, we will be covering our fiber preparation concept. Kevin, next slide.
Welcome to Season 3.
Welcome everybody again to episode number 7. I am joined today by both Eric Beckert, Dr. Eric Beckert, I assume, from Fraunhofer IOF. Hello.
Hello.
How do you do? How are you doing today?
Fine, thanks.
Good. And we are also joined by Arne Benfeld, Senior Product Manager from ficonTEC. Arne, how do you do?
Oh, I'm fine.
We've seen you, I think, at least once, maybe twice before on these events, right? And you are in our new studio at ficonTEC.
Yes, it's a very nice studio.
It looks very good at the moment. It looks a little better than it did before. Okay, thank you, Kevin, in that respect. So, for those of you who don't know, most of you may do already, but I will keep this short. What are the goals of the webinars? The goals of the webinars are to keep open our communication channels in this current pandemic situation. We try to keep these webinars short, so bite-sized events, so we can all get back to work. We don't take up too much of your time. That also means it's an agile format, so we can up our game, change the topics, move things around if needs be. What you will hear in this webinar is you will hear some general news and developments, not just about ficonTEC, but hopefully from the Fraunhofer IOF. You will hear about the products and technologies we will be talking about today in the topic of fiber preparation concepts. And of course, throughout this webinar, the viewers are invited to join the conversation by posing questions and listening to answers. Questions, please, into the chat, and I will do my best to bring them into the discussion as soon as possible and as soon as it makes sense. If we don't get any answers back to you today, we will do so after the fact. Next slide. Don't forget the giveaway. So I need to change the second question here. We have our usual giveaway. We will be sending out a lucky bag, or a Wundertüte, as the Germans say, to the lucky winner. How many Fraunhofer institutes are there in Germany? And the second question is, name me 2 other countries in Europe where there are also Fraunhofer institutes. So don't read the question on the screen, but instead name me 2 other countries in Europe where there are Fraunhofer institutes. Answers, please, into the chat. Okay, news. News from ficonTEC. This is a regular slide, or a regular point on this slide for ficonTEC. We are hiring across the board for sales, operations, marketing, service tasks in the applications group. If anybody wants to find out more, or you know somebody, we don't want to poach somebody from our customers and partners who might be watching, but if you know somebody who may be interested in a job at ficonTEC, you can go to our careers page online. You can also view some of the job descriptions on Stepstone, and also there's a number of them on Epic's Photonics job page online. ficonTEC will be at the 2 following events in November. PIC International in Brussels. There, Moritz Seifert from R&D will be holding a talk on through silicon assembly. That is also a webinar topic that we will be hosting, presenting on the 1st of December, I believe it is. And we are also at the Productronica in Munich from the 16th to the 19th of November. And I believe, Eric, you have maybe Fraunhofer is hiring as well. I think in our rehearsals, you mentioned that there were a couple of items. Please.
Yes, Fraunhofer IOF is in particular involved in quantum technology. So we are looking for quantum engineers and quantum physicists that can help us in the field of communication, imaging, and computing.
Okay, thank you very much. And they should go to the homepage, I guess, or contact you directly.
They can do both. Contact me, but also go to our homepage. We will have a job site in particular for quantum technologies soon.
Okay. And there's going to be an important announcement that we can't say anything about, right?
Yes, that will be probably the next webinar.
Okay, thank you very much. Okay, next slide. So on to the topic for today. We teased, I think, in webinar 2 in 2021, when we looked at the F300 and the CL1500 systems we offer and compared them. We also teased the fiber preparation concepts at that point in time with Arna's help in that webinar. We want to revisit that topic today with support from Eric, with a bit more information out of the LASCLAD project that we undertook together with other partners and the Fraunhofer IOF. And we will see some of that material today mainly in the presentation from Eric. Eric is the best person to present this information to you. As I say, we want to revisit this topic and bring you up to date on where we currently stand. Eric, please take it away.
Okay, thank you, Greg. Next slide, please. So first I start with a very short introduction of the Fraunhofer Institute for Applied Optics and Precision Engineering in Jena, Germany. It's the town of industrial optics, and that's why our research institute is also covering the full value chain of optics and photonics manufacturing, from the optical and mechanical design to the manufacturing of very specific optical components and putting them together into complete system, characterizing them and bringing them into dedicated applications. Next slide. I myself am an engineer, mechanical engineer, and I'm the head of the department Optomechanical Components and Systems. What do we do in this department? We integrate and assemble small, mostly optical systems. This is in particular where we also collaborate with company ficonTEC, where we focus on alignment, on assembly stations. We very often go into very dedicated environments such as space and aviation. We have a side activity about additive manufacturing, printing of functional materials, and printing of polymer-based optics. And when we go to the next slide, we will see that to do so, we have a technology pool that covers the packaging of optics. We bond optics by means of laser-based soldering. We assemble very dedicated oven-like assemblies to temperature leveling of nonlinear media. We have a quite interesting branch of CO2 manufacturing. This is something that I will talk then into more detail about. And I already mentioned we recently focused more and more to quantum hardware. You probably know that the quantum era is at the start, and we as engineers support that by building quantum hardware, in particular complex photon source payloads for satellites, quantum computer components, and so on. Okay, so that is a potpourri of what we do. Institute and
quick question, Eric.
In my department, yes, please.
The quantum aspect of your role or your remit at Fraunhofer IOF, is that relatively new, or is it something that's been growing for some time?
I'm happy that I started this activity more or less at the Institute, which was something like 6 years ago. We built a specific entangled photon source for the European Space Agencies. Started with 3 people 6 years before. Now the branch is overall, not only my department, something like 50 to 60 people overall.
Okay.
So you can see a huge growth in this area.
Okay, thank you. Please continue.
Okay, so let's go to the next slide. What I want to talk about in detail in the next few minutes is fiber preparation. Fiber preparation using a laser, CO2 laser. CO2 laser is quite a versatile tool, since you can do a lot with this laser, in particular with respect to fiber preparation. You see various examples here. Let's go maybe from the right to the left. We can splice or weld fibers to other things. We can taper fibers using the laser, so changing the diameter. We can clean facets with the laser. We can polish or create ball lenses at the end of the fiber. We can cut fibers, cleave fibers, basically. We can remove the jacket, the coating from the fiber, and we can also collapse, for instance, photonic crystal fibers. So basically all necessary processes that are required to prepare fibers before they are assembled in the system can be done by one single laser source, the CO2 laser. And this is what I would like to show you in the following slides in the case of some examples. Why is the CO2 laser a versatile tool? The reason is the 10 microns of the CO2 laser interacts with a lot of matter, and the 10 microns in particular has a strong absorption in transparent components. So in particular in glass-like components, like a glass fiber. You can investigate that scientifically. Refractive index of media. The part is the dispersion, and the imaginary part is the absorption. You will find that for typical glasses, you have a strong absorption in the 10 micron wavelength range, which is actually the range where the CO2 laser operates. And you can even check that the polarization of the CO2 laser, like you have strong absorption even at quite high angles of incidences. This is shown in the lower graph where there is plotted the absorbed power, or let's say the temperature that is generated by the absorbed power. And you see that even up to inclination angles of something like 60, 70 degrees, there is still enough power of the CO2 radiation absorbed in transparent objects that they result in a significant increase of the temperature of this transparent thing. And of course, we use this energy to melt glass or transparent media, or to ablate something from these media. So the absorption of CO2 laser is the basic functional principle that we use here. And you know, the CO2 laser is one of the most longest laser tools around. It is quite cheap. Still, it really makes use, in particular, with respect to glass manufacturing. And
Eric,
if we go, yes, please.
We know, probably most of the viewers know, we can use, at least for some applications and some materials, we can use ultra-fast lasers nowadays. Why would you not want to use an ultra-fast laser in this sort of application space?
Of course, you can also use ultra-fast lasers for, in particular, ablation, but also welding processes. We, by the way, also do that in Jena. As you can imagine, with ultra-fast laser, you have much smaller foci, so doing ablation or welding takes more time, much more time than using the CO2 laser. And for a lot of processes, the CO2 laser is just enough. So you do not have to buy an expensive femtosecond laser system. You still get good manufacturing results, even with a cheap CO2 laser. And when talking about CO2 laser, we have to rely indeed on very power stable CO2 lasers. And this is where the CO2 lasers also made advancement over the last year in providing quite stable power, which is needed for some of the processes that I will show later.
Okay. I imagine that ultra-fast. They're not very good at ablation, actually, are they? Right? It's a cold process, of course, speakingly in inverted commas. So you have to think about material throughput if you're trying to remove material rather than just modify it. Okay, thank you. Please continue.
Okay, what is maybe important to notice, the CO2 radiation is absorbed at the surface of transparent components. This results in the application cases where you can use the CO2 lasers, welding things onto the surface of components or ablating something at the surface of transparent components. When we talk about the femtosecond laser, there you are indeed able to deposit the energy inside the transparent material, there where you focus into. So there you can in particular weld inside optical material or at embedded interfaces between optical components. This is maybe the big difference between the CO2 laser and the femtosecond lasers.
Cool, thank you.
Okay, so let's go to the next slide. Now that we know that CO2 radiation is absorbed at the surface of transparent components, I would like to show you some examples what we do CO2 laser. You see, we start here with fiber stripping and cleaving. Very important processes in the automated fiber preparation in assembly lines, since you know the fibers they have to be prepared and stripped and cleaved before they, for instance, can be put into V-grooves or in front of any type of emitter. And this is exactly what we do with the CO2 laser. We ablate the jacket coating from the fiber. We create different types of beam shapes to do so. You see on the left how the ablation results might look like if you use Gaussian top hat or line profiles. But we are also able to ablate the glass material of the fiber itself. And this allows us to cut the fiber or to cleave the fiber, and you see examples for that on the right. On the top picture, you really see that we ablate more and more glass from fiber. It's starting from the right and then moving to the left, actually. And the most left ablation result is short before the fiber breaks, and breaking is exactly what the cleave is. You create the facet of the fiber. This can
At that point, have you already gone through the core with the laser beam?
At the most left ablation result, I think we are already through the core. It depends on what tension you apply to the fiber. It might break before you reach the core, or it might break after you reach the core. Depends on the tension that is on the fiber. Since it is a non-touching process, in contrast to traditional fiber cleaving, where you use a diamond blade to create a small crack in the fiber and then break it by tension, the laser creates this initial crack without any mechanical contact to the fiber. This means you can also cleave very small, tiny, and fragile fibers. You see an example in the center, 40 micron fiber would be very difficult to cleave with traditional technology. You would rather result in a lot of tiny glass pieces regarding that. And you can even apply the laser at very dedicated geometries. You see on the lower picture, there is a fiber welded to an end cap, and you can make a cleave very short at the fiber very close to the surface of the end cap. By mechanical means, it would be very difficult to go with a diamond disc so close to the end cap. So the laser is very versatile to place it wherever you need it, actually. And when we go to the next slide.
One question from my side.
Yes,
Do
please.
you see a difference if you do some processing on single mode fibers, multi-mode fibers, or polarization maintaining fibers?
To be honest, they all are cleaved in the same way, so creating more or less deep crack with the CO2 laser and then breaking them by tension. So there is not really a big difference between those types of fibers. It becomes more interesting regarding the dimension of the fiber.
No. Okay.
So single mode fibers versus large area or large diameter fibers. And there it's interesting, the bigger the diameter of the fiber is, the more difficult it becomes for mechanical cleaving, but still the CO2 laser works quite well even for large diameters of fibers.
If I take Anna's question a little further, on the one hand, we see in the middle image on the right, we see a little bit of, I think, Anna, you described this as mushrooming in our discussions beforehand, right?
Yes.
So there's obviously some thermal process going on when you're trying to cleave this filaments as small as this. Taking Anna's question to the next level, what are the difficulties in trying to cleave, let's say, a PCF, a photonic crystal fiber?
It's true, of course, the CO2 laser is a, let's say, hot ablation in contrast to femtosecond lasers where it's made a rather cold ablation, let's say so. Means we have really indeed a thermal impact onto the glass surface, and that is shown particularly at very tiny geometries like this 14 micron fiber. You see this mushroom effect, and yeah, this has to be taken to account. Sometimes it's not really relevant regarding very small dimensions. It might become an optimization issue.
Okay. One last question for me, as much as for anybody else. Can you quickly describe to us the function of an end cap?
Yeah, an end cap that we, for instance, see at the lower picture on the right is used in high power lasers to couple in high optical power into the fiber. You have to imagine, if you focus directly onto the core of a standard fiber, then you have a high power density on a small area. And in order to increase the area and have a lower power density at the same level of power, you use an end cap, which is actually a big planar rod that you attach to the facet fiber. And due to the beam propagation from through this big rod, you have a larger incoupling area at the facet of the rod instead of the facet of the fiber. In order to do so, you of course have to provide a good connection between this glass rod, the end cap, and the fiber itself. We aim for a monolithic glass to glass transition there, and this is what I will show you in the next slide, hopefully. Splicing and tapering, since this is indeed the process that we use to attach a fiber to such an end cap. It is a welding process. So splicing means welding. Welding means we melt the glass by means of the CO2 laser to enable the bonding of two glass components or the melting of two glass components together. Beam shaping optic that is in particular designed to weld fiber to such an end cap is shown on the left picture. You see the laser beam, CO2 laser beam coming from the left top downwards. It is then redirected by a rotating tilted mirror and creates the flying spot on a circle, angular ring, and this angular ring is then put around the fiber and then focused, which you see on the right side of the optical scheme, onto the tip of the fiber and the surface of an end cap. And there you simply melt the end of the fiber and the very center of this end cap in order to put the two locally liquid glass materials together and weld them together. How that looks like in the real machine, you see in the center photo, where we have the fiber gripper that holds the fiber that comes from the top. On the bottom, you see the end cap in a holding device. And this is at the moment the process where really the tip of the fiber and the center of the end cap are liquid due to the radiation by the focused ring of the CO2 laser beam. And there you put the fiber and the end cap together. And how that looks like then in the final assembly, you see on the right, you see on the top, polarization maintaining fiber spliced to an end cap. You can see through the end cap onto the polarization maintaining fiber cross section. You see the stress rods and the core of the fiber. And this is a monolithic glass to glass transition between the fiber and the end cap. If we go to the next slide, we can see that this is not only used for attaching a fiber to an end cap, like shown on the picture on the top, but it is also used to simply melt a fiber and change the diameter of the fiber by means of pulling it on the two ends and creating the so-called taper, which is basically change of the diameter of the fiber. This is used to adapt mold fields in fibers or to adapt the fiber diameter to emitter sizes, things like that. The nice thing for the CO2 laser is that you can really process a broad variability of geometries. You see fibers or even capillaries, so tubes of glass ranging from single mode fibers to even 2 millimeters in diameter can be processed, and we can create tapers in length up to 90, 100 millimeter, something like that. We can process single mode fibers, multi-mode fibers, photonic crystal fibers, and so on. So with the CO2 laser, you can process a broad variability of fiber types, which is difficult to do with traditional equipment, since the traditional equipment is most of the time either suitable for single modes or only for small diameters and so on.
What sort of input powers for the CO2 laser are we looking at for the different processes here?
Yeah, we typically use CO2 lasers here for these things that we see here in the range of less than 100 watts. Depending on the actual size of the glass parts that you would like to melt, you can even use CO2 lasers in the range of less than 50 watts.
And how long would a taper like we see here on this slide, how long would that take to generate that taper?
If we look at a taper that we see here, that might take up to a minute or something like that. Yeah.
I presume there's an automated process you worked out the parameters, you tested it. There's an automated process that carries that out for you automatically.
That's definitely true. Tapering must be an automated process. You have to have a very precise movement of the one side of the fiber versus the other side of the fiber. So you have two motorized stages that pulls at one and the other end of the fiber. And this is absolutely mandatory to create a precise taper by this technology. So yes, it is definitely automated.
Okay, thank you.
Okay, then let's move on to the next slide, which shows a much more advanced assembly, which is actually a pump combiner for high power fiber lasers. There you have the task that you have several sources of light that are used as a pump light for a active fiber laser. You have to insert the optical power into the multimode fiber, active fiber, and you can do all the processes that are needed for creating such a pump laser by the CO2 laser. So you can strip and cleave the fibers, the individual pump fibers. You can put them manually then in capillary. You can collapse the capillary onto the fiber bundle. You can taper it down to the final diameter so that it matches the diameter of the multimode fiber, and you can finally also weld this tapered fiber bundle to the multimode fiber itself, all by using single CO2 laser source. I think there was a question by Friedel about something.
There was indeed. Let me read it out to you. Friedel Bachmann. Hi, Friedel. How are you doing? Friedel asks, when cleaving a fiber, what is the accuracy and reproducibility that can be reached for the cutting angle? For example, when you want to do it, the ideal angle of 7 degrees or so. And then also for turning the angle around the optical axis. For example, in the case of polarization maintaining fibers. I'm not quite sure what he means there. Maybe he means, okay, he literally the question is, and turning angle around optical axis in the case of e.g. PM fiber. And also he asked, what is the flatness of the cut and the surface quality that can be attained?
Yeah, good point by Friede. First, if you remember how beam shaping setup can look like for the CO2 laser, you can imagine that adapting the design, you can change the cleaving angle by simply adjusting it based on the optical design of the beam shaping of the CO2 laser. So we can work at the traditional 8 degrees or at 0 degrees. What's the actual accuracy that we can achieve? I have to admit that I don't have a specific value, but I think I don't have a specific value at hand. I would have to ask my colleague. Yeah, maybe we can get back to that after the webinar. Regarding the cleave quality, it really depends on how much ablation we do with the CO2 laser and how much is then created by mechanical braking using the tension in the fiber. As said, that depends on the fiber diameter and also other parameters. We indeed create surface qualities that are sufficient for splicing, where actually the surface quality has to be quite good, although it's a thermal process. Yeah, but I don't have the actual values at hand also, but
Okay.
we can get back to Friedel about that later.
Okay, thank you.
Okay, and that brings me actually, I think, to the last slide. In a common project between ficonTEC, IOF, and NIFORCE, we were investigating in particular stripping and cleaving using the CO2 lasers. The CO2 laser, we were aiming for single fibers with exotic dimensions, in particular larger diameters. But in the collaboration with ficonTEC, we were in particular aiming for fiber ribbons, stripping the fibers inside the fiber ribbon and then cleaving the fibers to provide a cleaved fiber ribbon to an automatic alignment and assembly towards a silicon chip. You see, we created a breadboard for that. We are currently in the process of deriving first prototype of an OEM device that can be integrated into ficonTEC machines. So please look out to the fact that ficonTEC in the future will be able to provide fully automated complete fiber preparation in their fiber assembly machines.
we have a video which shows to an extent the results of the LasCloud project. Maybe we can quickly cover some aspects of the project. That the project has now been completed, I believe, right? And you will
Yes.
find the viewers will find on our projects and initiatives page, you will find a short note about what the project covered and what ficonTEC's role was. Nyfors is a company that's based in Sweden, I believe.
Yes.
And can I assume that some of the process types that you have described to us and some of the steps you have described to us in your previous slides were also aspects of this project that were developed or utilized within the project?
Yes, exactly. So we also have a long-lasting collaboration with the company Nyfors. They even sell a device called Smart Splicer that can splice and taper fibers using the CO2 technology, and
Okay.
now they expand their portfolio also to stripping and cleaving.
Okay. Okay. How long did the project run for? And it finished about a year ago or 18 months ago.
It was a 3 years project and it finished something like half a year ago, I think.
Okay. So we have a short video, and some people may have already found this on our website. Kevin, we can roll action, please, on the next slide. And what we demonstrate here is there are two separate processes here. Or there's the strip and cleave aspect, which we have put to. Anna, correct me if I'm wrong. Right? There's a strip and cleave process going on here with a CO2 laser on a 12 fiber ribbon. Is that correct?
I think it was a 16 fiber ribbon. 16
okay.
channel.
I need to improve my counting. And then there's a second aspect here, a very separate step at the moment still, I think, but we're looking at maybe bringing it together, insertion into module, right, into a fiber connector, and there we are actually quite agnostic as to which connectors we can address.
So what we put in or what we did in the second section of the video is inserting the prepared fiber ribbon into an empty MPO connector. And the next step then will be filling it with epoxy and cure it in an oven.
Okay, and I believe I spoke to Moritz some time ago, but I believe there has also been they have successfully done this with a two-tier connector, so two ribbons into the same connector.
That's right. We also did it now with a two-tier connector. Means we have two lines of fibers. And this is also demonstrated that this can be automated.
And what happens to those fiber tips that now poke out at the end of the connector? What would be the normal step here that maybe we would also apply in a fiber preparation concept system? Yeah. They would be cleaved again, is that correct?
After curing it in an oven, they will be cleaved and polished.
Okay, actually, if I remember correctly, so there's Kevin, next slide, please. There we go. So this is the slide that we showed in the second webinar 2021.
Exactly.
Where you have effectively also listed here then all the different process steps that we would envisage in a complete strip and cleave system. And if I remember correctly, there are maybe 2 or even maybe 3 separate laser steps within this.
So currently we do have the strip and cleave as a laser process. Then we do have the cut length as a laser process. And those were the main laser processes. After that, we prepare that the fiber will be placed in a V-groove, or it can be placed into an MPO connector or whatever. It's really depending on the customer needs.
So I believe we've had some interest from different people. We can't obviously talk about customer processes and requirements, but can we talk a little bit about what we are doing in this direction already? There was at least one topic that came up in our discussions.
So what we currently are doing is that we separate these inline processes into individual process steps. The most upcoming concern from fiber producers or fiber preparation companies are going from manual processing into automated processing. And this we are currently demonstrate that this is possible only for individual processes to release a little bit the concerns from the customers. That means we are developing now an R&D system where you can batch-wise automate these process steps to demonstrate the next step, that the automation is it's a next task which is coming up soon.
Next generation. And another aspect, I believe, is it for some for co-packaging and maybe some lighter applications, we're actually doing some work. Can you tell us a little bit about that?
What we are doing there, especially for co-packaging, is that we are placing fiber ribbons into V-grooves, placing a lid on top of it and cure it. Typically, these steps are done manually currently, and which can be now automated. And most of these steps are passive steps because the accuracy is given by nature from the V-groove. The only thing where we can activate it is to see the result, the outcoming result, if the placement was good or not.
Okay, thank you. If we go on to the next slide, there were a couple of other topics that came up in our discussions as we were preparing for this video. Something I think you mentioned, Anna, and that you have touched upon, I think, Eric, as well in your slides, is the requirement for cleanliness and intermediate cleaning steps during the series of process steps. Yes, I guess we're looking at removing remaining ablation material, making sure the cleaved ends are clean.
Exactly. If you cleave the fiber, if you remove the coating from the fibers, then you can have some residues at the fibers, and this is very important that they are very clean before placing them into V-grooves, because as I already mentioned, the accuracy is given by nature from the V-groove design, and if you do have some residues, then you do not place the fiber in the V-groove correctly, and then the result is not as good as expected.
And given the wavelength nature of light, right? If the size of that debris is half a micron, then you're missing your target already, right? So
exactly. What else we are doing now is, because some customers does have requests to create artificial ribbons. Means in all these projects we talked about ribbon fibers or fiber ribbons. What else can be done is that you do have a fiber spool, a fiber coil, where you spool the fiber, then you cut it into the length, then you cleave it, and then you create your own artificial fiber ribbons. This is also possible.
One last point I have on this slide, Eric has actually already touched on this point. Eric, I believe Fraunhofer IOF has recently ordered a new system from ficonTEC, or is in the process of receiving it, and your intentions are to utilize that system to take these developments further. Is that right?
Yes, that's true. We have in particular ordered a fiber stripping and cleaving module along with the device, where we collaborate together anyways to create such CO2-based OEM setups that can also be used in other applications.
So there we go. If anybody has an application that needs to be solved, you are welcome to approach either Eric or ficonTEC, Anna or myself then directly. Any other comments about the applications before we move on to the takeaways for the audience?
Nothing from my side.
Okay, then Kevin, next slide, please. So quick takeaways. We've learned from Eric that the CO2 laser is an incredibly versatile tool, has been for a long time. For materials processing and has been used for fiber applications for some time, but we have seen recent improvements in performance, in power stabilization, and of course in the levels of automation that are available today that help to provide a route to automating many difficult processes. I'm not going to go through all the points on this slide, but we have seen stripping, tapering, cleaving applications that can all be concatenated into an assembly process, for example, for creation of fiber ribbon. We are also looking at full automation and integration into assembly infrastructure of these process steps, so that instead of individual steps, maybe with manual transferring between different machines, that we envisage an entire line that is capable of pulling all these processes together and generating a final product. And of course, something we have touched on already is to an extent, we are very much connector agnostic. So the connectors with which we create those fiber wovens are, at this point in time, I don't think we have a problem with whichever type that is. Okay, thank you. Then quickly, next slide, then a quick roundup. If you want to find out more about ficonTEC, you can go to our webinar page, follow the QR code. We have recently, you're registered anyway, so you have access anyway, but maybe you can pass on the information to others. All of the previous webinars on our website are now freely available. We will be continuing with this next series. I believe the next webinar is due on December the 1st. There will be again another one on December the 8th. On December the 1st, we will be looking at through silicon assembly applications. You can, of course, also go to our homepage. You will find the webinar page. You will also find a blog, ficonTEC Insider is what it's called. We occasionally add new entries into that blog to keep you up to date on developments. And of course, anytime, feel free to get directly in contact with ficonTEC, either locally within Germany, within Europe, or at any of our other locations. Kevin, next slide, please. Around the globe, in the US, in Estonia, in Ireland, in Shanghai, Shenzhen, and Thailand. We will have some news in the short term regarding our activities in the USA, and there will be more demonstration of what that means when we attend the Photonics West event in 2022 at the end of January. Again, okay, last slide. Thank you, everyone, to everyone involved. Kevin, thank you for taking care of the technical side. Eric, Fraunhofer IOF, thank you for your contribution, very valuable. Anna, from yourself as well, thank you. I hope that was useful to everybody. And somebody has just arrived at the end of the webinar. I'm afraid they are too late. I'll let them in anyway. If you want to follow up and see this webinar again, or you missed the start, we will post this webinar online latest within the week, ideally within the next few days. Watch our LinkedIn feed or watch our webinar page. Again, to our viewers, thank you everybody for watching, and to our guest speakers, thank you indeed. Goodbye.
Bye.
Bye-bye.